Hey guys, welcome back to my channel. This is Bharat, and today we're going to study about a new problem, a line segment intersections. So before proceeding to the problem statement, I would like to briefly tell you an example so where you can use this problem and this algorithm which we are going to study. So consider this map. This is a geographic information system that consists of information about rivers, roads, and cities, which are labeled by the black dots here. So this has information about three different types, three different entities, and if all these entities are combined, the map look like this. So seeing this map, it is much complicated because uh, roads are below the roads are below the names, and there's something clumsy. It look like clumsy. So most of the geographic information systems split this map into layers, which I will show you down here. So the first thematic, we call it as a thematic layer. The first thematic layer consists of names of the cities labeled by the using a black dot there, and the second thematic layer consists just roads. So when we combine these, we get our full final map. So if you want to go to from suppose we want to go to Vancouver to Calgary, you will just look up the positions of them, and then overlay this map over this, and then you can see the road connecting those two areas. So in this way, we are going to use the geographic information systems. So what when you overlap these maps, there are certain points of special interest where we need our focus, where there should be a clear uh, distinction between them. Like when we overlap the map of river and roads, we will get some intersection points of those roads and the rivers. At those intersection points, we have to clearly specify them, because it creates some of the chaos there. So how can we find these intersection points in maps like this? So that's our problem statement. So suppose this dotted lines, consider them as a river, and this line is a road, and so any road or river, consider them as a set of line segments. So this is line segment, this is a line segment, this is a line segment, this all constitutes the road. In the same way, we will also divide the river as a set of line segments, and we join both of these sets and create a superset called S. So what's our problem statement is, given a set S of n closed segments in a plane, report all intersection points among the segments in P, in S, sorry. So when we get these intersection points, we will also get the due to this we also get the endpoints of the line segments also, which we are not interested. So after getting all these intersections, we will just remove the intersections which are endpoints, and we will get the exact intersections what we need. So this is our problem. So what's your first solution for this? Just brute force. Take any two pair of lines, check whether they are test whether they are intersecting. If they are intersecting, report the intersection, right? This algorithm takes big O of n square time. It is also optimal in one sense, where there is where the situations where you know that definitely there will be intersection between that pair of line. It will be optimal in that situation only. But in our case, we will have only a few intersections only, because consider this case itself. We have only few intersections between the roads and the rivers only. We don't have many intersections. So using this brute force approach is not very appropriate. So we need an algorithm which is output sensitive. That means with that depends upon the output. The time complexity should be depending upon the output. What is the output here is intersections, number of intersections. So here I'm going to present a new algorithm for you that is going to be an output sensitive. That is plane sweep algorithm. Before I introduce you to this algorithm, let me give you some terminology about this algorithm. So we have a plane that has a set of segments. So we will be starting from the upper part of the plane. Uh, we will be sweeping a line L down from upper part of the plane to the down. So here is shown the line L. It is moving down. What is status? Status is a set of segment intersecting the sweep line. At a particular instant, consider this instant. These is a state. These four segments are in the status of the intersecting sweep line. What are the endpoints? We can call it not just endpoint. We can call it as event point. The endpoints of the line and the intersection points are called the event points. At these particular points, we should stop, we should halt our process and test for the intersections. Until then we will not stop, we just sweep down. So this is terminology involved in the sweep line algorithm. So let's go into deep. So when the sweep line algorithm is started, the sweeping line will start at the upper part of the upper end of the plane and will start sweeping downward. So when the sweeping line reaches a upper end point of a line, this is a line and this is the upper end point of that. Let's check what's happening. So what should happen, what's happening to. So when the sweep line comes to this upper end point, this is a endpoints are also a part of event point, so the sweep line stops there. And now it will check for intersections between the lines which are adjacent to each other. If it finds any before that, it will add this sj, this segment, into our status and checks for intersections between the lines which are adjacent to each other. That means this is going to check the intersection between si and sj, sj and sk, sorry, sj and this segment, sk and this segment, and this in this way this sweep line will test for the intersections, and if it finds any intersection, it will add to our event queue. So what happens when the sweep line reaches an intersection point? When the sweep line reaches the intersection point, we should reverse the order of the those two segments in our status, because consider this line just above the intersection point, then these two lines are adjacent, and these sj and sk are adjacent, and sk and sl are adjacent, and sl and sm are adjacent. But when now consider the sweep line just below it, what happens? This and this are adjacent, sj and sk are adjacent, and sl and sm are adjacent. So there is a reverse of adjacency in this after moving below the sweep line intersection point. So the order of the segments should be reversed in our status. So the third event point is the lower end point of a line. When a line reaches a lower end point, we should delete this SL from our status list, and we should test for the what do you call intersections for the line, which is left and right to the line SL. Those are SK and SL SM. So we should remove the line SL and we should test for intersections for SK and SM. That's it. So these are the three kinds of event points that happen while we sweeping down to the. In this way, we're going to test for intersections, as we are also halting at the point of intersection, that is that itself is an output. So this algorithm is going to be an output intensive algorithm. So in the first glance, it seems confusing why we are sweeping these lines and why we are doing this, because we only want to test the line segments which are pretty much close to each other. We don't want to test line segments those are at this end and at this end. That's no need, right? That's why we only uh, or we don't want to test the line segments which is at this end and at this end. So we only test the line segments which are pretty much close to each other in their y coordinate sense and also their x coordinate sense, because we are only testing the adjacent lines. By doing this, we will definitely get all the endpoints. So what are the degenerate cases? What if the line in the in our line of the set of line in our set of line segments is horizontal? When we have a line which is horizontal in our segment set, we will place the point which is left in the event. We will place this point which to the left as first in our event queue, and to the point to the right as second in our event queue. So the consider this case as just for the understanding. I'm gonna tell you that just rotate the sweeping line about some 1-2 degrees, and just now come down. It will first reach the left point and then we'll reach the right point. So in the same way, we should add these 2 points to the event queue, such that the line stops at the leftmost point for the first time and next again stops for the rightmost point. Another degenerate case is when one or more number of when two or more number of line segments meet at a one point, like this. What are you going to do in these kind of situations? Well, this situation is well explained in the algorithm which we're going to study. So before that, I need to show you the data structures that are needed for implementing this algorithm. We use balanced binary search tree as event queue and status. So what is event queue? I haven't told you, right? Event queue is a list of event points. What are event points? Upper endpoint, lower endpoint, and intersections. Okay. What is status? Status is a list of segments that are currently part of the sweeping line. That's the segments which the sweeping line is touching. So what's the time complexity for creating this event queue is? So it should be sorted and created. There's a simple time complexity of big O of n log n. So what's the time complexity of inserting and fetching is big O of n log n, because it's a binary search tree. So what's the time complexity for the status structure for updating and neighbor search operations? Also big O of n log n, because it's also a binary search tree. So why are we using binary search tree? Because we can also use you can get a doubt that we can use a queue for event queue, but when we got in when we this that should be a dynamic structure, because when we found any intersections in the fly, we should have a capacity to add that in the middle of our event queue. That's why it is not appropriate to use a queue or heap structures for this. So it's definitely a case of balanced binary search tree. So this is how binary search tree look like. These all line segments appear as the leaves, and the internal node, as you can see the internal nodes, the rightmost leaf will appear as the internal node here. So Si is the Si, Sj, Sj, Sl, Sl. Now suppose you are at a point P, and if you are the point P, you will check this Sk segment is left or right to that point P. You will go accordingly to the different nodes, and again test it is left or right, and you will end up with a appropriate leaf. So in this way, this status data structures and status and event queue data structures work. So let's go into the algorithm. This is a global algorithm. 5 intersections. Input is a set S of line segments in a plane, and now we should output the set of intersection points among the segments S, with for each intersection point the segment that contains it. So what are you in first step? Initialize an empty event queue Q. Next, insert the segment endpoints into the queue. All the segments endpoints should be inserted in the queue, and when the upper endpoint is inserted, the corresponding segment information should also be stored. So when we insert all the endpoints, it creates a balanced binary search tree in big O of n log n time. So the first step completes in big O of n log n time. After that, we are going to initialize an empty status tree which takes a constant amount of time. After that, we will place a while loop. As long as the event queue is filled with some other event points, we should do this thing. What are we going to do? Determine the next event point in queue and delete that point, and send that point to a handle event point method. So in this way, we're going to find all the intersections. So I'm going to show you how handle event point method is designed. For the sake of understanding, I divided this handle event point method into 3 parts. The first part is here. It has 2 statements. The first statement is, let U of P be the set of segments whose upper endpoint is P. How can we get this set of segments? Means we already stored in our event queue the upper endpoints with respect to line, so we can get these segments from the event queue, or we already have information from our input. Now statement 2, find all segments stored in the status that contains P. They are adjacent in tau, that in the status. Let L of P denote a subset of segments found whose lower endpoint is P, and C of P denotes a subset of segments found that contains P in their interior. So let me give an example here. Consider this case itself. So for what are your U of P segments here? S2 is a segment here. It originates at this point and end at this point. So this is the upper endpoint. Suppose P is this point. U of P is S2 for this point. So what is L of P? Where L of P contains S4 and S5 because their lower endpoint is at this point. So what is C of P? C of P means the point should be contained within the line. So the point is contained in S3 and S1. So U of P is S2, L of P is S4 and S5, C of P is S1 and S3. In this way, we're gonna differentiate segments at a point. So this is a part 1 up to after the completion of part 1, we will get all the line segments that we need to analyze. On to part 2. If L of p union u of p union c of p contains more than one segment. So in this case, in the previous case, we have one u of p, two l of p, and two c of p. So union of them will definitely yield more than one segment. Then we report p as an intersection point together with lp, lc, and lu. The same. So it returns me. It reports means it returns p as an intersection. So if it doesn't, in case, we should delete the intersection, delete the segments that are that has p of p as a lower endpoint. Union p is in center from the status, and again insert the segments which has p as an upper endpoint and p is contained in the segments in status. The order of the segments in status should correspond to the order in which they are intersected by the sweep line just below p. If there is a if there is an horizontal segment, it comes lost among all the segments contain p. So this deleting and reinserting the segments of p reverse their orders if there is an intersection point there. As we spoke here at the point of before only, at the point of intersection the order of the line segment should be reversed. So this part of algorithm does that. So the part 1 we will get all the line segments. In part 2 line segments are analyzed, and if there is intersection that will be reported. If not, the line segments is ordered properly. In part 3 we will check for new intersections. After we have suitably arranged our line segments in part 2, we will go into check for intersections in part 3. So how gonna we check for intersections? There is a condition here. If neither the line segment contains p as an upper endpoint or in the interior of its line, then we will just that means it contains p as a lower endpoint. So we should, as we have discussed here, when the p is a lower endpoint, when the p is a lower endpoint, we should delete this line and check for intersections for sk and sm, right? So that is handled here. Then SL and SR becomes a neighbor, and we should find the intersections in SL and SR with respect to point P. So if it's not a lower endpoint, and if it is a upper endpoint or a point in interior of a line segment, then we have to S dash be the leftmost point in this set. That contains line segments which has P as an upper point or interior of the line segment, and SL be the left neighbor of S dash in status, and we will then find the intersection of this point with respect to this point, and in the same way we also find right side of that segment. In this way we're gonna find intersections. So what happens in this find new event method? In find new event method, if SL and SR intersect below the sweep line or on it and to the right of the current event point, and the intersection is not yet present in the event queue, then we are going to insert the intersection point as an event point in our event queue list. That's it. It just the find new event just tests for the intersection and do the same thing. So I think you have got some amount of idea what the hell is going on this algorithm, but I want to show you I will explain you this algorithm with an example that will give you a nice sense before going complex. For example, take this point. Take this set of line segments. So the sweeping line starts from here. Before that, for the start of algorithm, all these endpoints, this, and all these endpoints, upper and lower endpoints, are stored in our event queue and converted them into a balanced binary search tree. And our status queue, the status structure is initialized. And now, after initializing, there will be while loop, and while loop will call this handle event point method. So what happens in the first, in the handle event point method, it finds all the line segments required and categorized into U, C and L. So when the status line when the sweep line reaches to this endpoint, it has no other points intersecting, no other lines intersecting it. So, and this is the upper endpoint. So when we reach upper endpoint, this line segment comes under the set of U of P, and there is no L of P and C of P. So the part 1 is completed. So we found the U of P segment, and there is no L of P because no other line segment is intersecting P, intersecting the sweep line, and also no other line segment contains P in it. In this example, no other line segment contains P other than this segment, and the sweep line is here, so it is not intersecting any other line segments. So U of P is this line, L of P is null, and C of P also null. So going on to part 2, when we union these things, we get only one segment, so we are not going to report any intersection. Then statement 5, L of P union C of P, these both are null, so we're not going to delete any segments. Insert these segments. U of P has 1, so we're going to insert this segment now into our status list, which was initialized null before. So after adding this, part 2 is completed, and we will go to the part 3 here. We will check if this union is null. No, we have already U of P already contains 1, so if this union is not null, so we'll go to else condition here. So we will check for the leftmost segment in this union. We now just have only one line, so there is no leftmost segment for it, so we cannot check for the intersection. In the same case, in the same way, we cannot check for the intersection in the right way. So we have handled one event point. Now we will move to the second event point here. Consider this point. Now the line here will move down and come to this point and halt. Now again we will start from part 1. So now the P is this point, so U of P becomes this. There is no L of P because P is not a lower end point of any line segment, and no, there is no C of P because C is not a part of any line segment. And our status contains two line segments, this and this. I will show you the way. So U of P is one line segment, which is this we consider this point as P, so this is a U of P, and there is no L of P and C of P. So the part 1 is completed. We'll go to part 2. This union also gives 1 because L and C are empty and U has only 1, so this condition is not satisfied, so we will just ignore this statement, and then we'll come to the segment statement 5. L of P and L of P and C of P here again it is also null, so we will not delete any segments. We will insert the U of P in this line, and we will insert the U of P in this line to the status, and go to part 3, and we check for this condition, which is U of P union C of P is null. No, it is not null. We have U of P as one line segment in it, so it will go for the else part. And now U of the leftmost segment of U of P union C of P, we call it as S dash. So the leftmost segment in this case is this line itself. We don't have any P as an upper end point or point in the line, interior of the line. So, and SL is a left neighbor of S dash, but I think we don't have any left neighbor of the S dash in our status, because our status only contains 2 lines and there is no left neighbor for this, but we do have a right neighbor, this. So that will be tested in the next statement. So we will not find any intersections here, but now S dash, A double dash is the rightmost segment of in this set, So we have only one line, so that s double dash is that one line only, that is this line. But we have a right neighbor to that s dash in our status, because our status at this point contains these two lines, and u of p union c of p is this line, and the right neighbor of that line is this in our status. So we're going to find if there is any intersection between these 2 points. We're going to test that. If there is any, we're going to report. Otherwise we just again we have completed our program, so we just again start sweeping downward. In this way we're going to find all the intersection points. So what is the time complexity involved in this algorithm? As I said before, this is an output intensive algorithm, and it depends upon the number of intersection points also. So the time for the event queue creation is n log n, big O of n log n, and for every endpoint and an intersection point, that is intersection point means output, there are at least 3 operations that are performed on this data structures of event queue and status, that is the binary search tree. So those 3 operations may be finding the neighbor in case of finding the neighbor, insertion, deletion in the case of status, while if it comes to event queue, it may be finding the next element, insertion, deletion, these kind of operations, searching, these kind of operations will take big O of log n. So that depends upon the output also. So the total time complexity becomes big O of n log n, where n is the number of line segments, plus I log n, where I is the number of intersections. So yeah, we have reached an optimal algorithm for finding the intersections in the line segment. So now you have a graph like it, if you have a map like this, now it's a very good problem for you to solve. Thank you for watching a video. If you found it informative, please like, share and subscribe my channel, and thank you. Love engineering.